Welcome. In this video, we will finally take a look at the strong field Zeeman effect. Now, this is of course the case where the magnetic field that we apply onto the system, or the external magnetic field, I guess, depending on the situation. So the external magnetic field will be much larger than the internal magnetic field that comes from the motion of the electron. So the Hamiltonian for the Zeeman effect we have already seen. It is what I wrote down here. If you are unsure where that came from, you have to go back a few videos in the playlist. So how do we go about this? Now, what we always have to define whenever we're dealing with the Zeeman effect is, well, what is our perturbation? So in this case, since the Zeeman effect is much greater than the internal magnetic field, which basically means that the Hamiltonian, well, maybe let's do it here. The Hamiltonian from the Zeeman effect will be much greater than the one from the spin-orbit coupling. And since the spin-orbit coupling is of the same magnitude than the one from the relativistic effect, then we know that both of these will be much, much smaller than the Zeeman effect. And for that reason, we should take those two to be the perturbations. So we will have the base energy, which will be our unperturbed energy levels, which will include the Zeeman effect, and the perturbation on top of that will then be the fine structure, right? Which is the sum of these two. All right, so how do we find that energy? Well, we want to find the expectation value of this, right? We want to find its energies. So to do that, let's now take a look at this. So of course, all of these are in vectorial form, so L, S, and B. So let's take a look at the dot product. So when we dot product this, what will we get? The magnetic field will be in a particular direction. We might as well call it the Z direction, since it's kind of the direction that we always like to use. So if that happens, if we take the direction to be the Z direction, then we will only have the Z components from L and S. So we get LZ plus 2SZ. All right, and we would, well, be external, of course. And we would now like to find the expectation value of this. Now, the way to go about this, of course, is that in order to find the expectation value of LZ and SZ easily, we want to be in a base where their quantum numbers, so ML and MS, are hopefully good quantum numbers, right? Thinking back to what we saw in the in degenerate perturbation theory, where if we are in a situation like the hydrogen atom, where there is certainly much degeneracy, in that case, if we can find a good base, right, where our operators commute, then we will find, basically we don't have to use the mechanism of degenerate perturbation theory, and instead we can rely on the ones from non-degenerate perturbation theory. So how do we find those good states? Now, in short, we want to find those states that commute with the Hamiltonian, or those operators that commute with the Hamiltonian. So if our Hamiltonian is this, we can actually immediately see that LZ and SZ would commute with the Hamiltonian, right? So those are in fact good, our good operators. There are other ways of thinking about this. There are several, in fact. We can also think of the symmetry of the problem, because since we have the magnetic field in the Z direction, we will have this cylindrical symmetry, which is contrasted to what we had in the case in the previous video, right, for the spin-orbit coupling, where the symmetry was spherical. And that's why before the total angular momentum was conserved, but in this case, the total is not conserved, only these particular ones are. All right, so whatever your reasoning may be, we have decided to go in the base of MS and ML. And yeah, let's see what we get. So let's take the expectation value then. So HZ, this is going to be the energy, of course, from Zeeman. And this is going to be E over 2M times, now the expectation value of LZ, we already know, that's H bar over ML. And the expectation value of SZ, so we get 2 times, it's going to be H bar over times MS, and times B external. All right, so this is our our energy levels, but we can actually rewrite this, because if we take the h bar outside, we will get E h bar over 2m, which I hope you remember. This is in fact what we previously defined as the Bohr magneton, because it pops up a lot, and you know, we physicists are lazy and don't like to work anything any more than we have to. So if we now rewrite this right here would simply be the Bohr magneton. So this is our energy here. And of course, the unperturbed energy levels also have to include the base energy. So and what do I mean by that? I simply mean the minus 13.6 electron volt from the unperturbed, like completely unperturbed, not considering anything, hydrogen atom. So over n squared, and then we get plus Bohr magneton times the external magnetic field times ml plus 2ms. All right, so these are the unperturbed energy levels. What's going on now with the perturbation? So as we mentioned, the perturbation is going to be the fine structure. Fine structure. So we have to take its expectation value. So what is the fine structure? As we know, the fine structure is going to be the sum of the relativistic and the spin-orbit coupling parts. So we can here easily apply here the property where we can separate this. So we get the expectation value for the relativistic part plus the expectation value for the spin-orbit coupling. Now, the relativistic part is in no way affected by the magnetic field. So that means that this term will be exactly the same that we found before. For that reason, we shouldn't really concern ourselves about it. We already have the result. So let's now look for, maybe let's change the color if I'm gonna change topic here. Let's look for the expectation value of the spin-orbit coupling. Now, what was this Hamiltonian? Well, this Hamiltonian was 1 over 8 pi epsilon 0 times E squared m squared c squared times s dot L. So we have to take the expectation value of that. And then we have the expectation value of r squared, or 1 over r squared rather. But we already found that, so I'm just going to write the result. If you don't know where this came from, again, just go back a few videos and you will have a full explanation there. Times n cubed a cubed. All right, so basically all that we need to figure out is what is s dot L, or the expectation value of s dot L. But since we already picked a basis, we can write this out. So S is going to be Sx, Sy, Sz, and L is going to be Lx, Ly, and Lz. So the dot product of this is simply going to be Sx, Lx plus Sy, Ly plus Z, Lz. And we can separate all of these. So we can, this is going to be, damn it, maybe let's get over this. So this is going to be expectation value of Sx times expectation value of Lx plus expectation value of Sy, expectation value of Ly plus expectation value of Sz, expectation value of Lz. But what are these values? Well, we are on the basis of z. So these will average out to 0. I mean, each one of them individually will be averaging out to 0. So we are only left with this part right here. And we already know the value. So Sz is h bar ms and Lz is h bar ml. So basically, what we had here, this is going to be h bar squared ms ml, at which we can simply plug in here and we will have our answer. So this will be h bar squared ms ml. All right, so this is the Hamiltonian for the spin-orbit coupling. And of course, this is the energy, sorry, the expectation value of the Hamiltonian. And we already had the relativistic part, which we found before. So now let's put all of it together. And that is actually exactly problem 6.20. All right, there we go, I fixed it. So we want to now go ahead and solve Griffith's problem 6.20. So what we want to do is, starting from the results we found previously, so basically the energy levels for the spin-orbit coupling and for the relativistic part, we want to add them up and just get a nice formula for the strong field Zeeman effect, all right? And this, of course, we would then have to add to the energy levels of the Zeeman part itself, plus, of course, the base for the hydrogen atom, which is going to be the minus 13.6 electron volt over n squared. All right. I wrote down here some constants that we are going to need because we're going to need them anyways, and why Google them? So I just put them here. I don't know them by memory because I don't think there's much of a need to do that. So yeah. All right. So we want to add these two things together. Whoops. So let's go ahead. All right. So the thing is that adding them up is not as easy as it looks. Because, I mean, well, I guess it doesn't look easy. But yeah, we have a lot of things here that we don't really know what to do with. So one way to go about it is that we notice that there's this A, there's this En, which are these quantities that have like components inside of them, right? So what I mean is that both A and En have all of these 4 pi epsilon 0 h m blah, blah, blah. All of those things inside of them. And both of them are made up of the exact same components. Well, or almost, except for this N here. But we could see that if we plug them in, maybe we can then rearrange them in a way in which we could actually use alpha, which also has the same components, alpha being the fine structure constant. And we could hopefully, if this works out, we could find a way in which we could rewrite both of these in terms of alpha or alpha squared or alpha cubed or alpha whatever, and hopefully that's going to make things easier. So that is the hope. So let's rewrite A. So the Bohr radius, A, that is, this is actually 1 over A. So this is going to be the mass of the electron, m, E squared over, I think it's 4 pi epsilon 0, but I need to double check because I don't really know it that well. Okay, yes, but I need an h bar squared here. And this is going to be cubed. And then we need to rewrite this part right here. All right, so this is going to be minus 1 over 2mc squared times, let's see, what do we have? This minus, but since all of this is going to be squared, then this minus sign, of course, will be positive. So no need to worry. So we get times m squared 4h bar to the 4th power times e squared over 4 pi epsilon 0 squared, and then another one because it's squared. And I'd rather write it out like this, so it's easier to use algebraically later. And then we still have times 1 over n to the 4th power. And then we still have to multiply by this here. So 4n L plus 1/2 minus 3. All right, so now we want to see if we can write any of these as the fine structure constant. So the fine structure constant is this right here. So let's put it in the corner and try to write these expressions with alpha inside of them. So let's begin with a spin-orbit coupling. Now, to what order of alpha can we get? So let's analyze these things, or these both of these expressions, and see how high we can get. So the thing is, we have a lot of e squared. So we could go for alpha to the 4th power if we look at the e squared. We have a lot of 4 pi epsilon 0. We have 3 here and another one here. So we could also go to alpha to the 4th power. H bars, we also have a lot. What we don't have much of is C. We need 1 C for each order of alpha. So we actually can only go to alpha squared. And in the case for the relativistic part, it's going to be the same. We also have only c squared. So for that reason, we are limited and we can only go to alpha squared in both cases. So let's do that. Because that way we have alpha squared in both places, and that's nice. We can factor that out later when we add them up. So we want alpha squared. Now a good trick to do this without making too many mistakes is to just write what alpha is. Right, this is alpha and we want it squared. And now we just go back and we start, just canceling out every single thing that is in here, and then we write alpha squared, right? Don't just write alpha squared immediately and do it like in your head. No. Do it like this. Another good thing is that instead of writing this cubed, we are going to write it as this times the same thing squared. I would even go as far as writing it 3 times, but I'm short on space here. So this is going to be squared, because here you really don't want to make a dumb algebraic mistake. Believe me, you do not. Okay, so where do we get these things from? So e squared squared we can get from here. 4 pi epsilon 0 squared we get from here. H bar squared we can get from here. C squared we can get from here. And I think that's it, right? Yes, we have h bar squared, yeah. I mean, you could of course take this h bar squared, but you can't just scratch it here because this is actually a h bar to the 4th power. That's why I use that, but it doesn't matter in the end. All right, so this then is going to be alpha squared. And now we just write the rest of this expression. So 1 over 8 pi epsilon 0 times, well, and we already used this, e squared and another e squared, so e to the 4th power. Then we have this m. This m squared cancels out this m squared. Then we have this h bar squared, which will be partially cancelled out by this. So we get ml ms divided by l plus 1/2, l plus 1, n cubed times whatever is left from here, which is 1 over 4 pi epsilon 0 h bar squared. All right, that was a lot of work, but here we go. Now we want to do the same thing, but for the relativistic part. So here, how can we build alpha squared? So we want to build 1 over 4 pi epsilon 0 times e squared h bar c squared. All right, so let's see. H bar squared we can take from here, right? We can take 2 from here. Then we can take e squared 4 pi epsilon 0 squared from here. And then we need c squared from here. All right, now that we know where everything comes from, let's rewrite this. So alpha squared, and now let's go for the rest. So a minus sign divided by 2, and this m cancels out this. So we get an m here, and now times 1 over 4 h bar squared e squared over 4 pi epsilon 0 squared times 1 over n to the 4th power times 4n over l plus 1/2 minus 3. Whew, all right. So now we made some progress. Both of them now have this alpha squared, which they have in common, but they still have a lot of different like h bars and stuff going around, and that isn't quite that simple. But we can actually see that there is a common factor. Maybe it's not that visible right away, but let's go to the next page and it will become a bit more clear. So let's go here now, and let's now, all right. So now we want to start factoring these two expressions together, right? We want to add them up, and for that reason, we would like to factor out every common thing that we might have, every common expression, every common term. So let's take a look at them. So if we want to go for, maybe let's change the color here. So maybe let's go for blue or something, put a line, all right. So if we want to add ER, right, the relativistic and the spin orbit part, Well, what do we have in common? We have alpha squared, so let's just scratch it immediately. What else? Then we have m, so m here, so times m. Then we have e to the fourth, so times e to the fourth. We can then divide by 4 pi epsilon 0, which so e to the fourth. And maybe you can even, to make it more compact, I mean, it doesn't really matter, but we can write it as e squared, because we have this thing squared. So we have 4 pi epsilon 0 here and here, right? Writing 8 as 2 times 4, of course. So if we do that, we can also put an h bar here if we want. So we can get all of this squared. So e to the fourth, 4 pi epsilon 0, another 4 pi epsilon 0, and the h bar squared. All right. And we have the same thing here, right? So this squared, h bar squared. And there is still our factor of 2 that we can take from here and from this 2, right? This 4 we already used. So that's gone too. What else? Then we have still 1 over n cubed that we can take, right? This one. And we can take part of this. So I think that's all we can factor out. So what we are left with is ml ms from here divided by L over L plus 1/2, L plus 1. And then we still have this part multiplied by what survived, which is this 1 over 4 and 1 over n. So we get, well, there's this minus sign here, so be careful. Minus, we get minus this divided by 1 over 4n, so 1 over L plus 1/2, and then minus minus, so plus 3 divided by 4n. Okay, we're making progress. But what is this beast right here? We still have these constants. Let's go back and take a look at this. The energy levels are m over 2h bar squared, e squared, divided by 4 pi epsilon 0 squared. Times, of course, 1 over n squared. But if we don't consider that, then this right here is simply the energy of the first, of the ground state, right? So that's exactly what we have, isn't it? M divided by 2h bar squared, e squared, 4 pi epsilon 0 squared. That's exactly the same that we have here, except for the minus sign we would have to include. So we can rewrite this. So we can rewrite it as minus, well, alpha squared, of course, and basically all of this is simply going to be E1. Not bad. All right. And this is still going to be divided, of course, by n cubed. And we can also factor these two things together because we have L plus 1/2, L plus 1/2. So, you know, just to make it a bit more compact, let's use common denominator. So we get ML MS minus, and now we have to multiply up here by all the things that are not in the denominator, such as L and L plus 1. So we get minus L plus 1. All right. And now we have to divide all of this by L plus 1/2, L plus 1, and plus 3 over 4n. Whew. All right. So now, finally, all that there is left to do is to put in the value for the ground state of the hydrogen atom. So let's go to a new page and do exactly that. So let's copy this, go to a new page. And we know that the energy levels of the first state, so I don't know, what are we going to call this? This is the fine structure energy, so I guess I'll just call it that. Well, this energy, now we plug in E1 equal to minus 13.6 electron volts. So in the end, so fine structure, this will be, the minus signs cancel out, and we get alpha squared times 13. Actually, maybe it looks better the other way around. So 13.6 electron volts times alpha squared over n cubed. And then we have, well, maybe let's put 3 over 4n. And well, you can then use the notation that Griffiths uses. So you can use minus L. So basically you factor out a minus sign, but it doesn't really matter. Minus ml ms divided by L over L plus 1/2 L plus 1. Now, this does have a bit of an issue because what happens at L equals 0? Well, if L equals 0, you have to take this entire part as 1. All right, but we will take a better look at that in a future video so that we can understand it better and how it is that we have to go about it. But this is the formula that we need to find in this problem that Griffith's book gave us. Now, it was a lot of algebra, it was quite a bit of work, but if we go slow, it's all good. There's no problem. So I hope this video was useful. If so, please make sure to leave a like on the video, comment maybe if it was useful, and subscribe to the channel. If it doesn't cost you anything, but it really helps me out a lot. So I'll see you in the next video. Thank you very much for watching.